Okay, welcome to Josh and welcome Jake and welcome all of you who are watching this as an archive video. The plan today is regression analysis. It's a little different than what we've been doing before, although there is a hypothesis test involved, but it is a whole different kind of subject. We're going to be looking at comparing two quantitative variables that are not necessarily of the same unit system. So it doesn't have to be, meters versus meters. You can literally do height versus weight. You can't do that with a two-sample t-test, for example. It doesn't work. But we can look at these things. And we're looking for trends. That's the main thing is, are there going to be trends in the data and what kinds of trends? So in particular, what we're doing is we're doing linear regression. There are other forms of regression, but that would be a more advanced class. So we're going to be looking at, is there a line of best fit and what does it tell us? So if you look at the data, is there a linear correlation between the two variables? And that is the plan of the day. I want to set a couple reminders. First is the project is officially due Sunday. Strong recommendation that you get that done earlier so that you can enjoy Thanksgiving a little better. Tomorrow is the last day you can submit your project, tomorrow at noon, if you want me to review it, because I'm going to be heading off for Thanksgiving after that. And I need enough time to review it, because if everyone sends it on Wednesday, I won't have time because I'm teaching all day Wednesday and then I'm leaving. So tomorrow is the day you want to be submitting your draft, and then I'll give you lots of feedback on your draft and how it's going. After that, you could ask quick questions. I might be online some of the time. Thursday, I probably won't be online at all because it is Thanksgiving and I'm doing Thanksgiving stuff. I'm eating turkey. I don't know about you guys. Friday is also another day that I won't have much time. So just a note, don't expect too much from me other than short little questions Thursday, Friday, and Saturday. So just a big note. Don't submit your proposal, your draft after Thanksgiving. That's not going to work. And hopefully I've warned you enough on that. Second is we're almost done with the class. Okay, we're in week 10, which means in 2 weeks you have a final exam to take. So now is the time to start thinking about who your proctor is going to be. You're welcome to use the same proctor that you used last time, but you need to let me know one way or another who your proctor is so I can send your final to your proctor. I haven't written your final yet. I'll probably do that like on Sunday or something like that, is my guess, is start writing your final exam. That's my plan. But again, you need to let me know. I would say by next Wednesday, probably a good time to let me know. And again, you can let me know. I've already had a couple of people let me know already, but everybody needs to let me know pretty soon. So those are the main announcements to make about what's going on. Any questions, Josh or Jake? Any questions? No questions? Okay. What I want to do is I want to start out with a very, very important application for our area. So Josh and Jake, I always forget who's in our area, who's not in our area. What's important in Lake Tahoe? What is the data that everybody is most concerned about in our area?
Lake clarity.
Lake clarity, good. So you figured that out, right? Okay, if you live up here, you live here, right? Then you know lake clarity is number one. Okay, yeah. So the clearness of the lake. So I don't know if you realize, but the people who look at lake clarity and are in charge of it in terms of the research are UC Davis. So UC Davis scientists. And what I'm going to do is I'm going to share some work that UC Davis did and a little story about it. So let me share my desktop. And let me go find it. And that would be that one. There we go. So hopefully you can see that. Okay, so what I did is a few things. One is those lines, those are things that I put in. I put it in so I can talk about it today. The rest is all done for UC Davis. So we look at light clarity, and the big event happened in the year, around the year 2000. Might have been just before, but just around that time. And either of you guys know what happened in Lake Tahoe in the year 2000? Somebody important came here. Did you guys know?
President?
Yep, the president. Okay. And now that, do you remember your history? Who was it?
Bush?
Nope, no, because a little before. Clinton.
Clinton.
Yes, that was Clinton. That was President Clinton. And he came here, and it was kind of cool. One of my students actually served him his lunch while he was looking at what we're looking at now. And of course, everything to the right of this orange line, he wasn't able to see because that's the future. And what the UC Davis scientists did is they said, hey, look at where we are. And I'm not sure how many of you know what these little guys are, how they measure light clarity. I mean, these are called Siki dishes, and they're just little white plates. You drop in the water, they see how far it goes until you can't see anymore, they measure the rope. Any guess on how many measurements they took during each year so that they could have good data?
10,000.
It's a good guess. Here's a hint. I just smiled when I heard.
A lot.
You have it exactly? Should I tell you? 31.
Oh my gosh.
Okay. Yeah, you guys are smiling too. They did exactly 31. In fact, they took my class. But they wanted to make sure that every individual year followed a normal distribution because they took the average of 31 samples, and then by the central limit theorem, if you take the average of 31 samples, you have an approximate normal distribution. And if you have an approximate normal distribution, you could do all the stuff they wanted to do. Does that make sense?
Mm-hmm.
Okay, I was like, yes. So often they don't do their work right. Okay, you can't even imagine. Okay, so this is what, this is on the website. I just pulled it up 10 minutes ago from the UC Davis Lake Tahoe Clarity website. What they won't show you the lines because I put those in, and I just hand drew them. And again, ignore everything to the right of 2000 because we're going to think of things as they were a while back. And you will notice, if you look at the data, is there a clear trend? What do you think?
It's getting less clear.
Mm-hmm. Here's a trick question. What I did is I drew a line using this purple line. It's approximate. And here's the question. Is the slope negative or positive?
Positive.
Okay, what you didn't hear me is it was a trick question. Look at the y-axis.
Yeah, I see it. It's counting backwards.
It's opposite. So the slope is actually negative. Is that a trick question? I would never do that to you in a test, by the way. But again, I like, if I can, use real data. And this is the real data from UC Davis. So we got to take what they've got. So it's actually a negative slope. And if we look at the slope, let's look at, say, from 1970 to 1990. I'm going to draw something on that. So here's 1970. Sorry, that's supposed to be a right triangle. It isn't, but it's the best I can do. Okay, so that's a triangle. And the question is, what is the slope of this line? And this is something that you got from beginning algebra, so hopefully you still remember. How do you get the slope of a line? Do you remember? I can't get to. There it is. Yeah, y equals mx plus b is a line, but what is the slope? I'm looking for a number. So do you remember, hopefully slope is rise over run. So you want to look at the rise, which will be negative, by the way, because we're going from around 30 to, it looks like, around 27 or so. Oh, sorry, 22, not 27. So what is a slope? It's something you should remember from beginning algebra. I'm not seeing you jump in with typing, but maybe you're looking at it. Okay, yeah, around 7 over 20, maybe 8 over 20, 7 over 20 works well. Okay, except it's negative. So it's negative 7 over 20. If you turn that into a decimal, just doing it in my head, you get negative 0.35. Sound good? So we get negative 0.35, and let me write that down. And I'm going to write it down as negative 0.35 over 1. The reason I want to do that is I really want to think about it as rise over run. So now we say that this is rise over run, and the rise is the change in clarity. And the run is the years that have gone by. So what this says is that for every year that has gone by, that went by, the clarity on average declined by about 0.35 meters, which is about a foot, by the way. So I think I want to type that out because that's important. Okay, or at least how to figure these things out. For every year that elapsed, the lake clarity declined on average around 0.35 meters. Any questions on that so far? Okay, so now imagine President Clinton. And by the way, Feinstein was there too. There was like a group of heavy hitters at the first environmental summit in Lake Tahoe. By the way, a year and a half ago, a little less than that, they had an environmental summit, and President Obama was there. And the cool thing is, I got to go and see him. And I was literally about 25 feet away from the president. That was really exciting. And so he came to our environmental summit. And so was Brown, our governor. So they have these every year since then. All right, so now what I want to say is, first thing is look at the line and look at these dots. Okay, look at these Siki dishes. Is the line a good fit? What do you think? Is the line a good fit to the data? Okay, we're just looking to the left of the orange, pre-2000. Do you think the line is a good fit?
I mean, it goes through them pretty straightly, but
Yeah,
there's a curve under it.
Yeah, it's not perfect. It's definitely not perfect, but it's a pretty good fit, isn't it?
Mm-hmm.
It's definitely not perfect. And in fact, if you look at it, like around 1985, and then after that it went down, right? Clarity went up, in fact. That's what that means. So it goes up and down. Okay, it definitely went up and down, but there was a general trend from around 1968 to 2000 that was a declining clarity trend. And the good news is that President Clinton took statistics. I think that should be a requirement of every president. What do you guys think? It would be good if our presidents understood statistics so they could see data and understand how to make decisions based on data. And Clinton definitely was able to see the data. And what you would do next is you would look at this line, find the equation, and then use it to predict. So if we used it, for example, and we're just going to eyeball it for now, to predict the lake clarity today. Today is, hopefully you all know, year 2017. Then we see it's around up here. Do you see that? And that is about a lake clarity of maybe 13 meters. That would be very bad. Okay, if we had a lake clarity of 13 meters, then we have this mucky, gross lake, and Tahoe would not be blue anymore. And Clinton realized that. I'm not sure if he was looking at 2017. To us, that's important. In the year 2000, 2017 was nothing special. But the point is that they explained it to him. And I know because my student was his waitress and got to hear some of it. And they explained this data to President Clinton. And because of that, you may not know, but Congress passed a bill and he signed it. And it was a Protect Lake Tahoe bill. It was about $500 million. It's huge. And now look at post-2000. What do you notice about the lake clarity after the year 2000, after the bill was passed?
It's not getting worse.
It's not getting worse, okay? It's stabilized. It goes up and down, and most of that up and down, again, there's lots of factors that change lake clarity. One of the factors is weather, okay, is weather. My guess is when they look at 2017, our clarity is going to go down. Any thoughts on why?
Population increase?
Nope, no, because they've dealt with that. That's all the BMPs and stuff.
Big water year last year?
Yeah, weather. Not just big, it was a monumental water year. Okay. Fire, actually, we didn't have much fire at all this year. But we had a monumental winter last winter. And there was huge runoff, and we're going to see a drop. I'll pretty much guarantee it. But when we have a light year, it'll go back good again. So that's what we're seeing, is that there are different factors that influence lake clarity. One of them in the old days, pre-2000, was man. Is that clear? And that was what's going on here. Another one is weather, and there might be some others, but those are the two biggies, actually. So in particular, if we look at all of the data from 1965 to 2000, then we can see there's a pretty good variation in lake clarity, all the way from this top point here, which is around like 18 meters, to over here, which looks like around 31 meters. Pretty big variation in lake clarity over that period. But if you look at any particular year, now let me draw out some particular years, like say 1975 to 1976, and you look at the lake clarity, there's not much of a change in any 1 year span in lake clarity. In fact, if you look at the correlation looks like it's about -0.9. So it's a pretty tight fit. -1 is a perfect fit. This looks like about -0.9. If you square that number, you get 0.81. So what we can say is that 0.81 is R squared. Got it? The square of R. R being the correlation. So what we can say is if we look at all of this data, there's a big spread. But if we only look at 1 year at a time, on average, that spread is reduced by about 81%. Much less spread. And we could look at all different 1 year periods, and we'll find out that lake clarity spread is reduced by about 81% on average over all 1 year periods. Any questions on that? I eyeballed it, so that's from my general knowledge. So it's -0.9, by the way, Josh, because it's a negative. the slope and the correlation always have the same sign. If the data is a pretty good fit to the line, then you're around that 0.9, okay, or negative 0.9 if it's negative. If the data is a terrible fit, then you're going to be close to 0. If the data is a perfect fit, you'll be exactly 1 or exactly negative. This is not a perfect fit. It does go up and down, but it's a pretty good fit. Any questions on this idea here? One last thing, if you look at a line, as you all knew, is that y equals mx plus b is what you're used to. And we talked about that's the slope. Okay? B is the y-intercept. In this case, the y-intercept is useless. It has no meaning. Because the y-intercept means that the value of x is 0, right? And that would be the year 0. And the year 0 is so far from any of these data values that you shouldn't try to use the line to interpret the year 0. Okay, we only use the line to interpret values that are near the data. 2017 is not too far away. But you certainly wouldn't want to use it to interpret the year 20,000, because that's way away, or the year 0. In fact, between the year 0 and the year around 1800 or so, do you know what the population, the permanent resident population of Tahoe was? 0. Nobody lived here. Without technology, it's too cold and you die. Right? Just ask the Donner Party. Okay. It's not a place to live. The Washoe Indians lived down in the valley. They came up in the summers only. So the year 0 is meaningless in this case. Sometimes the y-intercept will be meaningful. Sometimes it will be meaningless. It's meaningful if the data values are near that and if the equation actually has meaning. You know, reading it makes sense. Any questions on this example? Okay, just a note. Oh, were they 81%? Okay, so first at 81%, 0.9 squared is 0.81. 9 times 9 is 81. Hopefully you can do that in your head, right? Okay, so that's where the 81% goes. And what it means is, what I mentioned again, is that there's a big variation in this data. If you look at the data, all the data from 1967 to the year 2000, it goes up and down by a lot, right? The low is around 18, the high is around 31. But if you only look at a focused year, then that variation, in particular, the standard deviation on average per year, is reduced by 81%. So much less spread of the data if you just look at 1 year. And you can't see all of the 1 year, but we do know that because they told me, the good thing is I live up here, so they told me that they did 31 samples, and that spread is 81% less than the spread throughout all the years. Does that make sense? Okay, that is probably the hardest part of this whole topic, is what that R squared means. Okay, any questions before I do another example? Okay, let me go and kill this. Okay. And let me do an example. Pop a new one up. I think I'll do some of these, not all of these, because we only have so much time. And let's go to clipboard, paste. Uh-oh. There it goes. That's where it got small. That's big enough. Okay. So it says, come up with two, and I'm just going to do one, real-life quantitative variables that have the following values of R. Then sketch possible scatter plot for it. So R equals 1. I don't know if you remember, I mentioned it already. So R equals 1 represents what about the data? What does it mean if R equals 1? Yeah, it's a perfect fit. Sorry if the screen is flashing. I'm not sure how to stop that. It's still flashing? Okay, so if R equals 1, it's a perfect fit. The only way you're going to get a perfect fit is if there is a mathematical equation that relates, that's linear, that relates the x and y. So an example would be degrees Fahrenheit and degrees centigrade. And hopefully you all know that there is a formula that if you know the Fahrenheit, you could figure out the centigrade. Okay, and you may not remember. Let's go centigrade to Fahrenheit, because then you might know it's 9/5 x plus 32. Does that ring a bell?
Mm-hmm.
So the scatter plot, first thing, it's going to have a y-intercept of 32. So that dot is 32. And then it's going to go up with a slope of 9/5. So I can't do it perfectly, but I'll do my best. Okay, so that line has a slope of 9/5, so that means if you move up 9, you go over 5. So if I go up to here, number, so that's going to be 41. And this will be 5. Any questions on that? And that way our slope was 9/5. Okay, so part B, same idea, except R is -1. I'm just going to drop dots to give you an idea. I'm not going to do the whole thing because we only have so much time. So if R is -1, the dots are going to slope. Now the slope doesn't have to be -1. It just has to be negative. So the dots could look like that. They could be steeper. But they're definitely going downwards, and they're on a perfect line.
Well, you have to decide on
Any questions on that? If R equals 0, that means no correlation. That means no correlation. So there are many, many, many things that have no correlation. So an example.
I'm good now. All I needed was
your exam score on the midterm. So how you did on the midterm, and say how many minutes the following year, exactly 1 year later, you were in the shower. Do you think that you could figure out your minutes the following year based on your exam score? Not at all. So the data would just be all spread out. So the data is just going to be looking like the night sky. So I'll draw the dots. Okay, so if we look at exam scores versus, let me draw an X and Y axis so you can see that. If you look at exam scores versus the number of minutes in the shower, it's going to look like that. Is there any trend that you could see between the two? Not really. Okay, it's just a bunch of dots all over the place. You don't see any line. You can't even imagine a line. Does that make sense? So that would be R equals 0. Okay, R equals 0.9. I'm not going to do because it's kind of the opposite of the example with light clarity. So that means it goes up. You have a nice correlation. And R equals negative 0.2. That means there's a correlation, but it's very, very slight. So the dots might look like. So do you see a trend here? Probably not. Do you see that? The data is all over the place. Maybe if you're stoned enough, you might see it going down a bit, but probably not. And that's what 0.2 is, negative 0.2. Does that make sense? So almost no trend at all. So I thought I'd show you that because, again, it is important to understand how these work. All right, so let me go to another example. Just 1 minute. This one's going to be with data. Okay, and the copy and paste never works well with tables. So that's supposed to be just a regular old table. Okay, the data below show the results of a study of 9 community colleges done that looked at the percentage of students at the community college who received financial aid and the percent of students who were business majors. Conduct the hypothesis test for the correlation and then perform a full regression analysis. So first thing, notice that these are 2 quantitative variables. They're dependent, which means we have one college looking at their financial aid, looking at their business major, another college, another college, another college. So because of that, we can look at regression analysis. So what I'm going to do is I'm going to write down the hypotheses. And the hypotheses are really easy because they're always exactly the same. H naught. I'm going to write equals 0, and then I'll fill in the blank. But because it's a Greek letter. Okay, that may look like a P to you, but it isn't. It's actually a Greek letter, and it's the Greek letter rho. Okay, and not coincidentally, rho is kind of the Greek equivalent of R. So what this says is that R is the sample correlation, rho is the population correlation. Remember that no, hypotheses are always about the population, never about the sample. And then, if we want to find out if there's a correlation, RH1 now let me draw it, is going to be rho is not equal to 0. So if the correlation is 0, then the whole regression analysis is useless, because that means the regression line is a terrible fit. It's not useful to predict. If the correlation is not 0, that means we do have a useful model as for regression analysis. Any questions so far? Okay, so the next thing, and you're used to this, is we get our calculator. So I recommend you get your calculator and do it with me. So I gotta reshare my screen. So here's the calculator. Let me clear out what I had. I'm gonna go to stat. I'm gonna go to edit. You're used to this. I'm gonna clear out L2. I'm gonna clear out L1. And then all I have to do is I'm going to type in the data for L1. That's the first variable, the financial aid variable. And that was 42, enter, and then 38, and then 56, and then 19, 40, 37, 72, 55, 20. Any questions so far? I do want to give a word of caution. The examples I give in class with data, never going to have a big enough data set. This is just for class learning, not to learn that, hey, you can get away with doing such a small data set, because you can't. Okay, but for learning, I don't want to spend all day typing in numbers. Okay, L2, 15. And then 17, 7, 34, 12, 15, 6, 9, and 27. Okay, so then we're going to go to stat, tests, go use the up arrow because it's a lot faster. And we're going to use lin-reg t-test. Okay. As I mentioned a bunch of weeks ago, kind of the last half of this class is learning all the menu items on this test. And here's lin-reg t-test. We're going to do all but I think 1 or 2 of them in this whole class. So I hit enter. X list is L1, Y list is L2, freak is 1, row not equal to 0 is what I want. Don't worry about reg equation. That's if you want to graph it using a calculator. And then enter. Okay, so we got all kinds of stuff here. In fact, I better write it down because I'm going to be leaving the calculator in a bit. So we have y equals a plus bx. This is a little confusing because you're used to b being the y-intercept. But with the calculator, what is b? Here's it. It's not the y-intercept. So what is b? If it's a plus bx, what does b represent? Yeah, it's a slope. So it's a little confusing. And don't shoot the messenger. It's the people from Texas that decided to make it go this way. I don't think I would have chosen this. If you do advanced math, it makes a lot of sense, but this isn't an advanced class. And the calculator is not for advanced stuff. But we just got to live with it. So we have a plus bx, and we're told that a equals about 36, let's call it 37, and b is equal to negative 0.5. And then we're also told p. P is not 5.0. It's 0.0005. So if p is 0.0005, what is the result? What's the conclusion? Just in general, you know this from every hypothesis test. So what's the conclusion if p is 0.0005? Yeah, we reject. Strong statistically significant evidence. Okay. The rest, we're not going to do much with. T, notice it's a t-test. So it's the same distribution that you're used to from a long time ago. We're given r squared is 0.84. That's important. We're given r, negative 0.9. So about the same as the Lake Clarity one. Okay. So it gives us everything we need. That's the good news. Calculator gives us what we want. Any questions? All right, so now I'm going to go back and we can start typing. So in particular, lost it. There it is. There is strong, statistically significant evidence to support the claim that there is a correlation between the percent financial aid students at a college and the percentage of business majors. Any questions on that? I notice it was negative. Okay, so does that mean that if you start giving more financial aid, you're going to lose business, you're going to lose your business majors? What do you think? Yes or no? Bo, I'm not sure what that means. No. Okay. No, yeah, it does not mean that. And this is really important because that's a causative state way of saying it. It does not say that this will cause that. Be careful about using any words that are causative. So you can't say, if you do this, then this will happen. You can't say that. You can't say, we're losing business majors because we have more financial aid. Okay, that's not okay with regression analysis. Okay, it might be true, it might not be true, so you can't say it. Okay, instead, you just say that there is a correlation. Notice that strong evidence does not necessarily give you a strong correlation. Sometimes you could have strong evidence and a weak correlation. That just meant your sample size was very large. And similarly, you could have weak evidence and for a strong correlation. That can happen too. So note the difference between evidence for the correlation and the strength of the correlation are different things. Any questions at all on any of this so far? Any questions? Okay, so because there is statistically significant evidence, that means you're allowed to do the rest of regression analysis. So in particular, for example, let's just make something up. A college that has 50% financial aid students is predicted to have, now I got to work this out. Well, we know that A was 37, B was negative 0.5, so it'd be 37 minus 0.5 times 50, which is 37 minus 25, or 12. 12% business majors. Any questions on that? So I just thought, let's use a prediction, and you can use the regression line to make a prediction. Notice that 50% is not very far from the data values. We have a data value of 55, another of 56, we have one of 40, so it's okay, and one of 42. So it's not unreasonable to use a line to predict for 50% because it's not far from the data values. All right, next, let's interpret the slope. So again, the slope was negative 0.5. So what that says is that for every additional percent of financial aid students, the college has the percentage of business majors. Tends to go down by 0.5%. Notice the word tends to. Okay, that makes it so you're not doing correlation. You're just doing tendency. Okay, the y-intercept was 0. It may not have much meaning because the y-intercept is pretty far from any of the data values. Do you see that? There is a 19. So if you want to stretch it and talk about the y-intercept because it's not that far from 19, you could say that the best prediction for a college that, well, if the y-intercept means x is 0, so that means the college has no financial aid students. Is that the college will have, what was it, 37% business majors. So there are some colleges that don't have financial aid students, not a lot of them. Usually they're for-profit colleges that aren't accredited. Then you wouldn't get financial aid. There aren't very many of them, no. Kind of a rare thing. Any questions at all on this example? Notice that R squared was 0.84. So that means that there's a pretty wide variation in business major percent, college by college. But if you only look at colleges that have a specific fixed amount of financial aid students or percent, then the variation decreases by 84%. Any questions on that? Okay, so you want to see another example? We'll do one more maybe. The nice thing is once you've seen an example, they're all kind of the same. Okay, you're given data and you plug it in. Sometimes they'll give you the results first. All right, so let me do another one for you. Let's go to select. Oh, missed it. One more try. There we go. And let's pop one in. Let me go find the one I had. Okay, so let's put this guy in. Okay, so suppose that the equation of the regression line that models the relationship between the amount of money X you can charge in dollars for your 1-hour massage shop, okay, for the 1-hour massage, and the number of people per week Y who come into your massage shop is given by Y. See that little hat on top? You read that as Y hat equals 251 minus 2.5X. And if the correlation is R equals negative 0.92. So R squared here is 0.92 squared. Any questions on that? R squared is 0.92 squared, and 0.92 squared is about 0.85. You can stick it in a calculator and you can see that. So let's interpret this 0.85. So we can say there is a large variation in number of customers in the shop per day if we fluctuate. Not sure if that's how you spell it, but hopefully it's not too bad. The cost. If we fix the cost, then on average, the variation in customers is reduced by 85%. Okay. Any questions on that idea? Any questions? Okay, part B, use the regression line to predict how busy your shop will be if you charge $50 per massage. So the hint is this is like the easiest of all problems. All you have to do is plug in 50. Do you agree that's easy? So let's plug in 50. And that just tells us that we get 251 minus 2.5, I believe. Let me double check. Yeah, 2.5 times 50. And you can stick that in your calculator. 2.5 times 50 is 25 times 125, 125. So 251 minus 125 is 126. Hopefully I did it in my head right. Any questions on that? So that means that our best prediction for the number of customers we'll have in our shop if we charge $50 per massage is 126 customers per day. Any questions on that? Okay, the interesting thing, I was just going by and I happened to see it. Locally, I saw 2 shops for 40 bucks a massage. I don't know, if that's normal or not, but I saw that today. Okay, so interpret the slope in the context of the study. So first thing, you are responsible for remembering your basic algebra. What is a slope? Put in the chat box. What is a slope? Rise or run. Good. But what is it? I want a number here. What is a slope? So the definition of slope is rise or run. What is the slope for this problem? It's given. That's a hint. You don't have to do anything except move your eyeballs. Not 1/50. It's literally written somewhere. So if you're doing any arithmetic, you've done it wrong. Yeah, almost. Negative 2.5. See the minus? So slope is negative 2.5 or negative 2.5 over 1. Okay, and remember that's the rise or run. And the x is the amount you charge. So that means if you charge $1 more, the y is the number of customers you have. And that is about 2.5. Remember, these are averages, so it's okay to talk about 2.5. You can't have a half customer, but you can have an average of a half a customer. So what we can say is that for every additional dollar that the shop charges, we can predict a loss of 2.5 customers on average. Any questions on that? Any questions? Okay. Do you know what they call this? I don't remember your majors, Megan and Josh and Jake, but do you know what they call this if you're a business major? This line? Diminishing returns, good guess, but that's not what diminishing returns are. The line itself, the 251 minus 2.5x. If you're a business major, you're supposed to know it. If you're not, then you have an excuse. Anyone know? It's called the demand curve. That's the demand curve. So if the price changes, then what is the demand for the product? In this case, the product is massages. And this is if you ever wondered how do you get a demand curve in business, this is how you get it. So if you want your demand curve to be linear, you do a lin-reg t-test and it'll give you your equation. So you look at the best fit of the data. And that's the demand curve. You could do something similar kind of in reverse to say, well, if it's this price, how many shops would you expect? And that's the supply curve. So, but this is the demand curve. Okay, y-intercept. Does the y-intercept have meaning? The y-intercept is 251. What do you think? Think business. Any thoughts? Yes or no? So does y-intercept have meaning in this idea, in this case? I'm not seeing you all answer. Yeah, it's 251, and is it meaningful? Okay, and the answer is probably not, because what that means is that you would charge $0 for your massage shop. You're in business. And any shop that charges $0 per massage is out of business. So it doesn't really make any sense at all. If you charge no money, well, of course you're not going to charge no money. No one gives free massages at a massage shop. So it's probably meaningless in this case. Any questions at all on this example? Any questions? So a couple takeaways is, one is you only use a regression line if you have a small p-value for correlation. Otherwise, it's not useful. Another is never use words like cause or because or if this happens, this will happen. Never use those kind of words when you're doing regression line analysis, what we call linear regression analysis. Instead, you use words like we predict that, or there tends to be, on average this, but you don't use any causation words. So that's really important. You will be tested on it, by the way. Okay, so those are the main things. And the slope is a rise or run. So if you change x by 1, it's the predicted amount that y will change. But when you're doing on a test, don't write x and y. Write down what the meaning of x is and the meaning of y. Any questions on this? Okay, let me give you the word of the day, the secret word. And the secret word today is slope. The secret word is slope, because the slope is, if you have a regression line and it's a good model, the slope is always useful. The y-intercept may not be useful, but the slope is always going to be useful because it tells you how much you predict y to change if x changes by 1. It might be negative, it might be positive. The slope and the correlation always have the same sign. Not the same number, the same sign. So as always, I'm happy to answer any questions you might have. And that could be about the project, it could be about what we just did. Anything that you have questions on, I'll be happy to do. And I'm just double checking that it really was slope because I put in the quiz. I'm sure it is, so. Forgot to write it down, but my memory's pretty good. So any questions? Yep, that was correct. Any questions at all? Okay. As always, if you don't have questions, we can just say goodnight. But if you do have questions, I'll be happy to answer. Okay, and I think I'll say goodnight. Megan, you got any questions?
No, thank you.
Okay, well, thanks for coming.
No problem.
Forget the secret word, and please, you know, post questions about your project because that's the big thing coming, and send me your rough draft if you haven't already.
Perfect. You should be getting that at the latest tomorrow.
Okay, yeah, tomorrow's my day for reading them. That's why I want you. If I get it by noon, then I can get them all read by the end of the day for tomorrow. Because it takes me time.
All right, thank you.
Okay, thank you. And for all of you watching this as an archived webinar, thanks a lot for coming. And don't forget to get that project and do a really good job of it. It's worth lots of points. So take care, everybody.